Okay, okay, nice.
Okay, thank you. So we start the seminar at
Hmm.
2 5 in
Hmm.
order that the participants
Hmm.
get to the session, right? So we wait like 3 minutes,
A few minutes? Okay, okay. Nice,
and
nice.
then we start this.
Mm. So are you a graduate student or some faculty there?
What do you mean? So the participants are obviously students from the um, postdoctoral, but no, yes, postdoctoral programs or PhD,
Hmm.
master, even the how to say licenciatura, bachelor,
Undergraduate.
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 Yes.
I am an undergraduate. I don't know if you
Mm.
remember right away.
Oh, you're co
Hello
Yeah.
again.
Hello, hello. Yeah. Nice to hear from you again.
Yes, and
Yeah.
also researchers.
Mhm.
Mhm.
Nice.
How is Gilad?
Hmm?
How is Gilad Perez?
Oh, Gilad? I don't know. I think he's doing fine, and because I've been spending the past few months in the US, I don't quite know what's happening there.
Ah, right. Okay. I thought you were in Rehovot. Like,
Oh, I'm not. I'm in California. That's why, like in my emails, I was mentioning California time.
okay, perfect.
Mm.
Thanks for taking the invitation, by the way, before it starts.
Yeah, I just realized I don't know. I don't know what the Zoom link is.
Sorry.
Oh, I mean, I just yeah, just realized this morning that I did not know the Zoom link.
Ah, yeah, sure. Yeah.
Hmm. Yeah.
So, okay, here we go. Faith, we record the
Mhm.
seminar. It's good for you?
Yeah, it's fine. Yeah.
Okay. So, welcome everybody to another session for this seminar, Búsqueda de nueva física en aceleradores y el cosmos. Today we have the presence of the Dr. Fei Juan. He's going to present us the next talk. I'm going to give you a brief review from his work. So he's interested on dark matter and early universe. He earned his PhD in 2019 from the University of Arizona. After that, he joined to the UC Irvine from 2019 to 2022 for his first postdoctoral position. And nowadays he moved to Weizmann Institute of Science in Israel. So please go ahead, Dr. Feijuan.
Yeah, thanks a lot, Ren, for the introduction, and thanks a lot for the opportunity to present my work at the Benemérita Universidad Autónoma de Puebla. And today I'm going to talk about my recent work on cosmological stasis, which will include a theoretical overview, some model realizations, and phenomenological implications. And this talk will be based on these works, which are done in collaboration with different collection of the following people. Professor Kistinius, who is my PhD advisor, and Lucien Ertier, Du King, who I met when they were postdocs at Arizona, and Professor Tim Tate, who is my postdoc advisor at Irvine, and then my long-term collaborator, um, Professor Brooks Thomas from the Lafayette College. Okay, so cosmological stasis is a modified non-standard cosmological scenario. But before we talk about anything that's non-standard, let us first take a look at the standard law, the standard lambda CDM cosmology. We know that in our present universe, there are basically three types of energy component according to the equation of state. So we have vacuum energy, whose equation of state parameter is -1. We have matter, whose equation of state parameter Wm is 0, and radiation, whose W is 1/3. And using the Boltzmann equation for these energy densities, the equation of state parameter actually tells us how these energy densities evolves as the universe expands. So if you insert these values of W, we know that the energy density of the vacuum energy does not change when the universe expands, while the matter energy density scales like a to the -3. And this is because the energy density rho m is basically mass times the number density. While the number density goes like a to the -3, the mass of each particle does not change. On the other hand, radiation energy density goes like a to the -4 because not only the number density of relativistic particles goes like a to the -3, the energy of each relativistic particle, which is mostly kinetic energy, goes like a to the -1. And that's why taken together, rho gamma scales like a to the -4. So because of the way different energy densities scale, when we extrapolate the present day energy density back in time, we find that even though dark energy is the most dominant, most abundant component at the present epoch, matter was actually more abundant in the near past. And at even earlier times, radiation was dominant. And then together with the inflation and reheating epochs, which are introduced for other reasons, this picture forms the standard lambda CDM cosmology. And apparently, for most parts of the standard cosmological timeline, the universe is dominated by just one single energy component. And therefore, it is natural to divide the cosmological timeline into epochs characterized by the most dominant energy component. So going from the most distant past to today, we thus have the inflationary epoch dominated by vacuum energy, and then the reheating epoch, which is usually considered as matter dominated, and then the radiation dominating epoch dominated by a thermal bath of relativistic particles. And then matter-dominated epoch, mostly dominated by dark matter and the subdominant component of standard model matter. And finally, the present-day universe dominated by dark energy, which is often considered as some form of vacuum energy as well. Okay, and in this picture, these different energy components only have similar abundances near these transition points. However, this picture is likely to be incorrect in the presence of many kinds of BSM physics. And this is because a wide variety of scenarios for BSM physics actually predicts towers of unstable particles with a broad spectrum of mass, lifetimes, and cosmological abundances. For example, series with extra spacetime dimensions has KK towers. String theory has string moduli, axions, KK towers, and oscillatory states. Scenarios with confining hidden sector gauge group has bound state resonances. And if you generalize the idea of particles to black holes, we can also have primordial black holes with extended mass spectrum. So if any of these tower exist in the early universe, the dynamics across the entire tower can significantly affect the evolution of the universe. So let us take a decaying tower, for instance. So suppose we have a tower of matter states. It can potentially be infinite or bounded by a relevant cutoff. And the mass spectrum of all these states in the tower can, in general, be stretched across many orders of magnitude. And such states are generally unstable and can decay. Usually, the heavier states on top of the tower tend to have the largest decay width and decay first, and then the lighter ones decay later. The decays thus will proceed down the tower. And typically, for any state in the tower, the dominant decay mode is to the lightest states possible. Such decay products are in general like has a large amount of kinetic energy, and thus they're effectively radiation. So let us assume that the decay products are outside of this tower. For example, you can decay into photons or other light particles in the thermal bath. Then these dynamics across the tower can then be seen as a sequential process down the tower, which continually converts matter into radiation. Okay, so mathematically, the dynamics of this decaying tower is described by a set of coupled Boltzmann equations with source and sink terms. So there is one equation for each state L in the tower, and then a single one for the radiation component. And then using the Friedmann equation, one can re-express these differential equations in terms of the cosmological abundances. So here I have summed over all the abundance of omega L in the tower and write it as a differential equation for the total matter abundance omega M. And this sink and source terms now becomes the abundance weighted sum of all the decay widths. In our papers, we usually refer to these terms as the pump terms. So what do these pump terms do? Well, if there's no such pump terms, we know that the matter abundance always increase relative to that of the radiation when the universe expands. But when these pump terms exist, they will provide a way to pump energy from matter to radiation and thus counteract the relative growth. In other words, they tend to bend these curves in the opposite direction. So we just saw that cosmological expansion tends to convert omega gamma to omega m. On the other hand, the sequential decay across the tower tends to give omega m to omega gamma. Can these two effects balance? Well, this may seem too much to ask for, but what we find is that they can balance, and in fact, they do balance. And even if they do not start out by balancing, the system can quickly come into balance all by itself. it turns out that this kind of balanced solution is an attractor, and this is very remarkable because particle decay and cosmological expansion are like two very different things. One is particle physics, and the other is cosmology. So, in these circumstances, instead of having a picture like this, the universe may more likely evolve like this. Okay, where there can be an epoch in which the matter and radiation abundances stay constant and nothing needs to dominate. And in fact, any kind of abundance configuration can be possible, even though this is like a 50-50, but like any kind of ratio is possible. Okay. So this may seem surprising, but it turns out it naturally occurs for a variety of models and for a wide range of parameters. And we find that no fine-tuning is required because this is a global attractor, which means if the parameters satisfy certain criteria, such phenomenon may even be unavoidable. Oh, by the way, am I speaking too fast or too slow? And if you have any question, just feel free to interrupt me. Okay. All right, let's continue. Okay. So to be more specific, we can, for example, parameterize the tower in the following way so that you have a mass spectrum where the mass of the state in the else level is equal to m0 plus some delta m gap times the tower level L to the delta power. And we can parameterize the decay width such that the decay width gamma L is proportional to the mass ml to the little gamma spar. Okay. And then we parameterize the initial abundance such that the initial abundance omega L is proportional to the mass ml to the alpha power. And we find that stasis arises for all values of these parameters within this range when alpha plus 1 over delta is between 0 and gamma over 2. And this will happen regardless of the other parameters. Okay. And once we know our model, which tells us the values of the parameters alpha, delta, and gamma, we can actually predict the value of the abundances during the stasis epoch. So this is a prediction. And well, you may be unfamiliar with this kind of parameterization, but those are well motivated parameterization. So for example, the mass spectrum comes from the particle physics model that you have in mind. Suppose we are thinking about KK excitations of a 5D scalar field compactified on a radius on a circle of radius r. This delta can take values like 1 and 2 depending on the value of m times r. And if you think about bound states of Strohney-Couple gauge theory, you can take delta equals 1/2. And this decay width depends on the decay mode or the operator. Okay, so for example, if phi L decays into photons through this kind of contact operators, gamma can take some typical values like 3, 5, and 7. And then the other important parameter is this alpha. This alpha tells you how the initial abundance is distributed across the tower, and it depends on the production mechanism of the states in the tower. So typically for misalignment production, you have alpha negative, but for thermal freeze out, alpha can be either positive or negative. But if all the states are produced by the universal decay of an inflaton, you can take alpha to be 1. So in total, we shall have these parameters. Alpha controls the abundance, gamma controls the decay width, and delta controls the mass spectrum. And those quantities with superscript 0 suggest that they're just initial conditions. Okay. And yeah, if you're interested in more details about this kind of parameterization, here is a list of references in which this kind of parameterization is discussed in different contexts. Okay, now let us take a look at some numerical results. So here is one example. We choose the parameters alpha, delta, and gamma such that um, the matter abundance, our prediction of the matter abundance is exactly 1/2 during the stasis epoch. And you can call this like extended matter radiation equality. But the initial condition here is omega m equals 1. Then in this example, the universe starts with a completely matter-dominated phase, and then the fields start to decay away, and then the matter abundance start to decrease. And after just a few states decaying away, the system enters the stasis stage with the matter abundance that is very close to 1/2. And then at a later time, the system can exit this stasis epoch after the last few states decay away. This stasis epoch in this example persists for like from 15 to 20 evos, which is quite significant. And the duration of this stasis epoch is actually determined by our model parameters, like what is the value of gamma, delta, and how many states you have in the tower. Okay, so this is very remarkable. And you might suspect if this is very fine-tuned. So here we can show a bunch of different cases with different model parameters predicting different values of matter abundance during stasis. And it's clear that prolonged epochs of stasis can be achieved in many different scenarios. Okay, so stasis always emerges, only the stasis abundance changes. And by doing this numerically, we can actually find that the stasis solution is a global attractor. You can start with different initial conditions that is away from the stasis solution, but the system can always evolve and end up in the stasis epoch. The system can also start with the same initial abundance, but with different overall decay widths, and then it can go through different evolution trajectories. Like some of them approach it slowly, some of them can overshoot it and then come back, but eventually all these trajectories end up in the same stasis value. And finally, one can think about where does this stasis epoch arise in the cosmological timeline. And for this particular scenario, stasis can occur during the reheating epoch after inflation, so that the universe is reheated by the decays of all the states in the tower instead of just the decay of the inflaton. One can also imagine that the presence of like multiple matter fields can first lead to a early matter-dominated epoch, and then stasis occurs when the decays start in the tower. So those are different possibilities for this kind of stasis. Thus far, is there any questions? Okay, if not, I'll continue. So we have seen that a tower of unstable matter fields can give rise to oh, is there something in the chat? Oh, no question. Okay, good, thanks. So that's why we have seen that a tower of unstable fields can give rise to stasis between matter and radiation. So we're wondering, are there other mechanisms for this type of stasis? So other than fundamental particles, we find that we know that black holes can also be produced and populated in the early universe. And such primordial black holes, PBHs, are massive and non-relativistic, and they therefore belong to the matter component of the universe. And since primordial black holes can lose their, or actually black holes in general, lose their mass through Hawking evaporation, this can be an alternative way to pump energy from matter to radiation. So we can ask this question. Can a population of evaporating primordial black holes give rise to cosmological stasis? well, to investigate that, let us first look at the similarities and the differences between particle decay and black hole evaporation. Well, from the perspective of energy transfer, particle decay and black hole evaporation are quite similar as they both convert matter into radiation, but they do have some small differences. So let us first look at the Boltzmann equation for single matter field and population of black holes with a single mass M. Okay. You can see that if you think about a co-moving volume, the matter field changes its energy density by decreasing its co-moving number density. On the other hand, the black holes change their energy density by losing their masses. So they change their energy densities in different ways. However, in the Boltzmann equation, like they both have some little piece attached to this rho here. So we can identify this term here with the decay with gamma here and treat this term as an effective decay width. And recall that in our previous formula, the decay width scales like m to the little gamma's power, and gamma is positive for particle decays. In this effective picture, the effective decay width of a black hole, based on the formula for Hawking evaporation, it actually amounts to gamma goes like m to the minus 3. Okay. So we'll have a little gamma that is negative. And this is reasonable because heavier particles tend to decay faster, but heavier black holes tend to be more stable and evaporate more slowly. In fact, it turns out that the parameterization that we just used before to describe a tower of particle states is also applicable for describing a collection of primordial black holes with different masses. What we have just seen is that primordial black holes have an effective decay width that goes like m to the minus 3, which means this little gamma here will be minus 3. And for the mass spectrum, primordial black holes have a naturally continuous mass distribution. And so this amounts to having delta equals 1. And to have an initial abundance distribution that follows this scaling relation, we just need this mass distribution in the initial time to scale like m to the alpha minus 1. And actually, we will need alpha to be negative to achieve stasis. And interestingly, this kind of situation naturally arises if primordial black holes are formed with the collapse of a scale invariant power spectrum. And just to be a little more specific, we will assume that this initial mass distribution follows this power law within a mass range m min and m max. And this m min will be larger than 0.1 gram, which is a lower bound set by CMB measurement. Basically, it tells you how big the Hubble parameter can be after inflation. Okay. And this m max will be smaller than 10 to the 9 grams, such that all the black holes will evaporate before BBN. Okay. So for black hole masses within this range, the Hawking temperature will be much higher than the heaviest mass in within the standard model. This like typical temperature will be larger than like 10 TeV. Okay, and as a result, all the evaporation products are relativistic and can be considered as radiation. Given the previous examples with decaying matter fields, I don't think I need to convince you that the population of primordial black holes satisfying this kind of parameterization can also give rise to stasis. So let us just look at a few examples in our numerical results where we use the maximum mass range possible start our system with a PBH dominated universe, but the PBH abundance drops as soon as the lattice black holes start to evaporate. The PBH abundance then will approach a stasis value for a while until the heaviest primordial black holes evaporate away. And the total number of EFOs during this stasis epoch can be roughly estimated using this formula, which is essentially determined by the mass range and the power alpha of the mass distribution. And it is worth mentioning that this kind of black hole stasis was actually first noticed by Barrow, Copeland, and Little more than 30 years ago. And around that time, it was just a cute model of a universe filled with black holes and radiation. However, now that we know much more about cosmology and constraints on primordial black holes, we can study the phenomenological implication of such a scenario. Okay, so let us first look at some of the basic constraints on our parameter alpha. And just like in the previous case, the stasis solution enables us to predict the abundance and the equation of state during stasis once we know the value of alpha. For a physical sensible range of primordial abundance, which means the omega BH should be between 0 and 1, alpha is constrained between -5/2 and -1. On the other hand, this alpha also depends on the cosmological history when the primordial black holes are formed. In particular, the quantity alpha is determined by the equation of state WC of the entire universe during the PBH formation time. So this relation here tells us that alpha lies between -2 and 0 for physical PBH formation scenario, where the equation of state WC is between -1/3 and 1. This is basically saying that you cannot really producing PBH when the universe is undergoing accelerated expansion. Taken together, this alpha can only be between -2 and -1, which means the primordial black hole abundance can only be between 0.4 and 1 during stasis. And indeed, this quantity is like the omega BH bar and W bar and also WC. They're all correlated as a function of alpha in our scenario. And this correlation tells us that the existence of a primordial black hole induced stasis epoch modifies the cosmological timeline, not only just by itself. Okay, it actually implies a sequence of modification to the standard cosmological timeline. And this timeline goes like this. We can start from the inflation epoch. After that, there is a PBH formation epoch whose equation of state parameter WC determines the shape of the PBH mass spectrum through the parameter alpha. And after that, the PBH might slowly dominate the universe. This may or may not happen. So that's why I'm using dash line for this square. And this depends on the initial PBH abundance. And then when the evaporation starts, the universe enters the stasis epoch caused by the evaporation of primordial black holes. And finally, after the most massive primordial black holes evaporate, the subsequent cosmology will coincide with the standard cosmological timeline. Okay. And such a cosmological timeline can also be shown conveniently by looking at the evolution of the co-moving Hubble radius. So here's a sketch of a few examples with some different alpha, and in which we have segments for PBH formation time, PBH domination time, and PBH stasis, and the slopes of each epoch depends on the equation of state parameter of that epoch, which are ultimately fully determined by the parameter alpha. Observationally, such modification to the cosmological timeline can be constrained by CMB measurements on the inflationary observables, uh, which are the spectral index NS and the tensor to scalar ratio R, as they depend sensitively on the cosmological expansion history. So, depending on the inflaton potential, varying the parameter alpha can affect how much the inflationary observable is compatible with the CMB constraints. And in addition to the inflationary observables, the sequence of non-standard epochs also modifies the spectrum of the stochastic gravitational wave background from inflation by modifying the value of the scale factor at the time when the perturbation modes re-enter the horizon. Uh, so what happens is that if the equation of state parameter W is 1/3, meaning the universe is radiation dominated, the gravitational wave spectrum will be flat, and this is actually the case in the standard cosmology, where you have this completely horizontal spectrum. However, if the density perturbations enter horizon when the equation of state parameter is not 1/3, the corresponding part of the spectrum will be an increasing function of k if W is larger than 1/3, or a decreasing function of k if it is smaller than 1/3. So what this tells us is that a gravitational wave spectrum that would be scale invariant if it is produced in the radiation-dominated epoch will be modified if the PBH-induced stasis occurs. Okay. For example, if you take this value of alpha, alpha equals minus 3/2, the spectrum will look like this, where we have like different segments corresponding to modes entering the horizon at different time. So during modes entering the horizon during the radiation domination will be responsible for this flat part, but if they enter horizon during stasis with a W smaller than 1/3, it will go down, and for PBH domination, it will have this steepest slope. And for this particular choice of alpha, the formation epoch actually has W equals 1/3 again. So this part is again flat. Okay. We can also increase alpha. The overall trend is similar, but the slope for different epochs will change. And this part here, which corresponds to PBH formation with W smaller than 1/3, will go down even more. So this will be not so good for the observations. However, if we increase alpha, and actually if we decrease alpha, making this WC for a PBH formation to be larger than 1/3, this part of the spectrum can actually go up. And this means the sequence of non-standard cosmological epochs not only provide a way to evade detection at frequencies relevant for the spaced or ground-based interferometers, they actually also provide opportunity for gravitational wave experiments at ultra-high frequencies, like in the megahertz or gigahertz frequency. Moreover, by shifting the mass range around, the location and the depth of the deep can also change. And in some cases, it further decreases the detection prospects. But there are also situations like these ones, which can even provide opportunity for future space-based experiments. Okay. Thus far, is there any questions from the audience? Okay, if not,
Yes, I have a question.
okay.
Well, two questions.
Mhm.
Uh, Firstly, what an amazing talk. Uh,
Thanks.
Secondly, I want to ask about vacuum energy. My question was about if vacuum energy can be transferred into the radiation.
Mm, yeah, so can you be a little more specific?
To be honest, I don't know about the subject, but my point, well, the question is about if Higgs mechanism
Mhm.
uh, can explain the vacuum energy transferring to uh, radiation energy.
Can, can Higgs mechanism explain vacuum energy? Oh, sorry, I haven't get to the vacuum energy part of the stasis scenario yet, but um, vacuum energy. Well, there are scenarios like, for example, warm inflation, in which the vacuum energy can transfer energy into radiation, just kind of like decay. It's because of some um um I mean, as long as the scalar field that is responsible for the vacuum energy has coupling to the other particles in your model, there will always be a way to transfer energy from the vacuum energy directly to to radiation. Yeah, I'm not sure if I understand your question.
Thank you.
Okay, yeah, thanks for asking. Oh, there's another question in the chat. Could you explain a bit more why state of stasis occurs in cosmology? So why do they occur? So I guess you're asking about production mechanism of these states. Um,
Yes.
um, sorry. So you're talking about how can these states be produced, right? Well, the production mechanism. Okay, so I think I mentioned a little bit before. Let me find that slide. Um, okay. Yeah. So here I'm presenting a framework, and like the production mechanism do depends on specific model that one can think about. For example, if you think about misalignment production, if you have like a 5D field, right? You have misalignment production, and then after compactification, like you really let me see. So usually the okay, it's for misalignment production is like this. You have you have a field, and then the initial value of the field is displaced from its minimum, and so that once they start to oscillate, they can have they can behave like matter. And if you think about like the thermal freeze out scenario, you can imagine that at the beginning you have some fields that is in thermal equilibrium with the thermal mass, and then they freeze out. But once they freeze out, they can slowly dominate the universe. So if you have like a tower of states that goes through the freeze out process, and then you can have at a later time a tower of matter fields that is non-relativistic and can dominate the universe. And those states can also be produced from the decay of inflaton. Just imagine the inflaton just decay into a bunch of those particles, like the KK states in the tower. Yeah, so there can be many different ways to produce these states. Um, so, I'm not sure. Did I? Okay, thanks. Yeah. So are there any other questions? Yeah, please feel free to interrupt me. And especially at this point before I jump to the material of a new paper. Okay, if not, let me continue. So thus far we have seen stasis arises between matter and radiation. It's natural to ask, like, are there other types of stasis? Well, in our later studies, we found that stasis can also arise between vacuum energy and matter, between vacuum energy and radiation, or even between vacuum energy, matter, radiation simultaneously, which we refer to as triple stasis. So for the rest of the talk, let me focus on this particular scenario and talk about a specific realization of vacuum energy matter stasis, where a tower of dynamical scalars. Okay, so in many BSM scenarios, it is very common to have a large collection of scalar fields whose zero mode values are initially displaced from their minima. And these fields can initially be frozen due to Hubble friction and later become underdamped and begin oscillating. And this kind of transition can be seen as a transition from vacuum energy to matter. And since for any scalar, this kind of transition occurs when the Hubble parameter is similar to its mass. Usually the critical moment is when 3h equals 2m. This transition, the transitions of all the scalars can form a sequential process from larger masses to smaller masses across a tower. So we're therefore interested in this question. Is it possible to achieve a prolonged epoch of cosmological stasis from such a tower of scalars? Okay. To study this, let us first warm up by looking at the case of a single scalar field. Let us consider a scalar with a mass m, and we can write down its energy density rho phi and its pressure p phi, and therefore the equation of state parameter w phi, and its equation of motion, which takes the familiar form phi double dot plus 3h phi dot plus m squared phi equals 0. And for the moment, let us consider a fixed background in which the scalar field is really subdominant, and therefore the equation of state equation of state of the universe is a constant w. And under this assumption, the Hubble parameter takes this form, h equals kappa over 3t, where this kappa can be related to the equation of state w. In addition, we also assume that the initial displacement of the field is non-zero, but the initial velocity of the field is negligible. So the field is not rolling at the beginning. And the evolution of the field then looks like this. Okay, the field is at the beginning is nearly constant. It rolls very slowly at the beginning, and then start to oscillate rapidly. Okay, the critical transition occurs when the Hubble parameter is close to the mass. 3h equals 2m is this moment here. And if we look at the equation of state parameter of the scalar field, we can see that in this so-called overdamped phase, w phi is very close to -1. Okay. Whereas in the underdamped phase, W phi, like, it actually jumps back and forth between -1 and 1, but the time average is actually approximately 0. So in this example, we can actually obtain a analytical solution for the equation of motion, which is described by this by the Bessel functions, whose order depends on the value of gap. Now let us consider a tower of such scalars phi L. Okay, for each field, the energy density, pressure, and the equation of state parameter, just like what we have seen before, and we also have a cosmological abundance for each scalar, which is simply rho L divided by 3h squared and Planck squared. We shall continue to use the same old mass spectrum, which is motivated by KK towers. And for simplicity, we shall assume that there's no coupling between different phi L's, and thus that each field has its own quadratic potential, VL. And then the equation of motion is therefore just n copies of the same equation that we have seen before. And for the moment, we shall also assume that the tower is dominating the universe, and therefore the Hubble parameter is completely determined by the total energy density of the tower, and the total abundance of the tower is 1. Okay. So we also need to specify the initial conditions. For the initial conditions, we shall once again take that the initial velocity of the fields is 0. And this is just for simplicity. And this is also consistent with many standard generation mechanism. For example, the misalignment mechanism. We shall also use the same initial abundance distribution, which means that the initial field value actually needs to scale with the mass ml in a particular way. Okay. And therefore, for a universe dominated by this tower, the overall scale can actually be parameterized by the ratio between the initial field value of the lighted state and the Planck scale, or equivalently, the ratio between the initial Hubble value and the largest mass in the tower. Okay. All right. With all the preparation, the dynamical evolution of our system goes like this. Okay. At the beginning, all the scalars are displaced from their potential minima and are all overdamped, but they will start to roll slowly due to a non-vanishing acceleration in their equation of motion. And each phi L then transition to underdamped phase when 3h equals 2m. As time goes, increasingly lighter fields in the tower begin to oscillate. And at any time t, there is a critical tower level, LC, that divides the tower into two regions, which can be treated as two different energy components. One is the so-called slow roll component, where all the fields are effectively all slow rolling. Those are the fields that satisfy 3h larger than 2m. And the other component is the oscillatory component, whose masses, which contains all the states with masses satisfying 3h smaller than 2m. Okay, so we have abundance for these two different parts of the tower. Can we achieve a stasis between the slow roll component and oscillatory component, which act like vacuum energy and matter respectively? To figure out this question, let us review what is required for stasis. We know that during stasis, the effective equation of state parameter of the tower W is equal to W bar, which is a constant. And therefore the Hubble parameter will take this form kappa bar over 3t. And as a result, the solution to the equation of motion for each phi L can take the same form as a single field case. And they can all be described by the Bessel function in the same form, but we just need to be a little careful about the mass dependence here. And with that, we can then calculate the total energy density of each energy component in our in the continuous regime. And for example, we can calculate the energy density of the slow roll component, which is just some factor times the integral, which involves some combination of Bessel functions. And notice that the integration variable here, tau equals m times t. This integral actually originates from summing over all the masses. Okay. Now, let us look at the integration limits. We have 0 here. The upper limit actually depends on the critical mass that separates the slow roll and oscillatory components. And during stasis, this boundary here is actually constant because h equals kappa bar over 3t. So this upper limit is actually constant. And this actually means the entire integral here is a constant if we are in stasis. And therefore, the only time dependence for this rho SR is hidden here. Okay, this 1 over t to the alpha plus 1 over delta. Now, recall the definition of stasis, which requires the abundance to be a constant. We know that rho SR goes like the inverse of t to the alpha plus 1 over delta. And we also know that the Hubble h goes like 1 over t. The definition of stasis then tells us the condition for stasis should be alpha plus 1 over delta equals 2. So we will expect that any tower satisfying this relation should give us stasis. And such condition also implies that the initial field value should follow should scale with the tower level in this particular way. Phi L goes like L to the minus 1/2. So here are our numerical results. Yeah, stasis does emerge. And for the same set of parameters alpha and delta, we actually can have different stasis values for omega SR, and thus also have different values for the equation of state parameter W bar of the tower. And indeed, in this scenario, we noticed a very interesting sensitivity to the initial ratio between the Hubble parameter and the largest mass in the tower, or equivalently, the ratio between the initial field value and the Planck mass. And this is unlike any previous stasis scenario that we have studied before. And it turns out that the larger the ratio h over m minus 1 is, the more slow roll abundance we have during stasis, and the stasis epoch can be more vacuum energy-like. And the universe also expands faster since the kappa bar, the value of kappa bar is larger. And this in turn also affects the duration of stasis. So when we estimate the duration of stasis, we find that the initial ratio not only appears here in the log, but also affect the duration through this value of kappa bar. So the duration for the same tower, the duration of stasis can be much longer in a universe with more slow roll components. So we have seen that if the tower dominates the universe, it leads to a stasis with constant slow roll and oscillatory abundance, and therefore also a constant equation of state for the entire universe. Is this stasis robust against the existence the existence of other energy component, especially since there's the dependence on H0 at the beginning. Let us then consider adding some non-interacting background fluid with a constant equation of state parameter. So here we choose different initial abundance for the background component and let it evolve together with the tower. And notice that in some cases, the tower can even start with a very small initial abundance, and the background, for example, here is like 90%. It actually dominated, can be the dominant one at the beginning. And we find that the overall behavior depends on two parameters. One is the equation of state parameter of the background, WBG. And the other is W bar, which is the equation of state parameter, which we expect to have if there is only the tower. And it turns out that if WBG is larger than W bar, the background component actually will inflate away. Okay, omega BG will go to 0, and we end up with the same stasis as the case in which we only have a tower. Okay, they all end up with the same stasis value. However, if WBG is smaller than W bar, the background component will eventually stay at a constant abundance together with the slow roll and oscillatory components. The system the system will the system still evolves into a stasis epoch, but the new stasis value for the solid curve here, for the slow roll and oscillatory components are modified to values that are different from the other one. Okay, the stasis values are modified. So why is that? To understand what is happening, we can take a look at the evolution of the equation of state parameter of the tower. So this is the evolution of W. So here we investigate many different cases in which we choose different background components with different WBG, but the tower always have the same initial structure with W bar equals -1/2. And what we have found is that if WBG is larger than W bar, the effective W of the tower stays at W bar. And therefore the background component will inflate away. On the other hand, if WBG is smaller than W bar, the effective W of the tower will converge to a new value, a new W bar, which we call W bar prime, and this value matches exactly the background value. And this is why the background component coexists with the tower without being inflated away. So not only do we see the attractor behavior, we also see a very interesting tracking behavior where the tower can adjust itself so that it has the same equation of state parameter with the background. Let us ask even more. What if the equation of state parameter WBG of the background is time dependent? Can we still have this kind of tracking behavior? So let us add a background component whose equation of state changes like a step function. So this WBG can go up and up again, or it can go up and then back down. And interestingly, we observe that the tower is always trying to match WBG, even if WBG varies rapidly. So this kind of tracking behavior is actually very robust. Now, comparing the stasis from the dynamical scalars with the matter radiation stasis that we mentioned at the very beginning, we observed that if stasis involves vacuum energy, the equation of state parameter can be extended to the region where W bar can be negative. On the other hand, we also know that the universe experiences accelerated expansion if W is smaller than smaller than minus one third. This means the stasis epoch can potentially be the inflation epoch. So there is a possibility of something we call stasis inflation, during which there can be a non-vanishing amount of matter abundance. And this possibility for stasis inflation is very intriguing. If such a stasis epoch can endure like roughly 60 numbers of epochs of expansion, it can in principle solve the horizon and flatness problem. In this scenario, the number is often related in a deep way to the hierarchies among the fundamental particle physics scales. For example, in the KK series, the number of epochs for stasis will depend on the number of states, the number of state levels in the tower. And the number of states in the tower is related to the compactification radius, the UV cutoff, and the number of compactified dimensions. Moreover, in this type of scenario, complicated potentials are in general not required. The dynamics of inflation will reflect the structure of the underlying theory instead of reflecting the shape of the inflaton potential. In addition, we have also seen that during stasis inflation, like any W bar smaller than minus one third is possible. We are not restricted to a W that is close to minus one. It also came equipped with a graceful exit. Stasis inflation can naturally end itself when the underdamping transitions reach the bottom of the tower. Finally, there can also be a non-zero matter abundance, or even together with radiation, that can be carried throughout the entire inflationary epoch. These abundances do not inflate away, and this may significantly change the conditions needed for reheating. And of course, any model of inflation along these lines would need to pass a list of tests, such as reproducing a nearly scale invariant density perturbations that is consistent with CMB data. And it also needs to satisfy applicable constraints on Lagrangianities and isocurvatures. And we also need to eventually reheat the universe, presumably from the decays of all these oscillating phi Ls after stasis ends. Nevertheless, stasis inflation is a scenario that warrants further exploration. Here's a summary. We have seen that stable mixed component cosmological errors, which is stasis errors, is indeed a viable cosmological possibility, and it can arise naturally in many extensions of the standard model. And this kind of stasis can be generated in many different ways, such as a tower of decaying matter states, a population of evaporating primordial black holes with a broad mass spectrum, or a tower of scalar fields undergoing transitions from overdamped to underdamped motion. And stasis not only arising naturally in these systems, it is actually a global attractor. This make it potentially unavoidable. And if the universe didn't experience that, we will need to ask why it didn't experience that. The phenomenological implications can also be tested against cosmological data. And especially for the stasis induced by a tower of dynamical scalars, the tower can exhibit a very interesting tracking behavior. And there's also a intriguing possibility for stasis inflation. Finally, there are some recent developments that are worth mentioning. In a recent work, Jonah Barber, Kistinis, and Brooks Thomas have presented a model in which stasis can be realized through the annihilation of a single particle species without using a tower. also have been introducing towers throughout the entire talk, but they managed to find a scenario that they only need one species. There is also a recent paper from Jim Halverson and Snap Pandya, which uses machine learning to analyze what forms of mass spectrum can give rise to stasis, and they were able to connect the stasis work, which is motivated mostly by KK towers to string activers. But in any case, in all cases, we have seen that the universe continues to expand, but the abundances can stay fixed. The time passes as measured in the number of epochs of expansion, but not as measured by the abundances. The two clocks, the abundance and the expansion, which are deeply related to each other in the standard cosmology, have completely decoupled during a stasis epoch. Okay, so this concludes my talk. Thank you.
Okay. Thank you so much, Faye, for your amazing talk. So can we pass to the questions? Feel free to open your
Yeah.
microphone.
I do have one, Faye. Hello again.
Mhm.
Okay, so maybe it's a sort of naive one, but using your stasis model, how would the dark matter production happen? Like in which phase of the formation of the universe? Maybe you did mention it and I got lost. And which model would be like consistent with it? Would you keep the extra dimensions Kaluza plane, or would it be like using, I don't know, dark sectors, or which production model for dark matter would you be using?
Oh, I didn't really mention the production of dark matter in our scenario. So this is like a separate question, but it's also worth studying. So yeah, in principle, like you can generate dark matter through like a completely different mechanism. It doesn't have to have anything to do with stasis, but the existence of stasis can modify your prediction for example, like the dark matter abundance and like density perturbations. So a general expectation is that if dark matter is produced before the stasis epoch, then the stasis epoch can in principle dilute the abundance of dark matter. It is also possible that the dark matter can be produced through the decays of the states in the tower. And in that case, it's a more complicated story. You need to take into account like how dark matter particles are produced, and because of those decays, you can even have very non-trivial phase space distribution of dark matter. But if dark matter is produced after the stasis epoch, then I wouldn't expect stasis to affect the production of dark matter. Yeah.
Okay, yeah,
And
makes sense.
yeah. Okay, thanks.
Someone else? Do you have questions?
So it could be, sorry again, like it could be any model, right? Like if it happens after stasis, then it could be pretty much any existing model. Like you do not require, for example, the Kaluza plane specifically. It could be any other
Yeah,
model.
yeah, you don't have to be. Yeah.
Ah,
Yeah,
perfect.
yeah. So there are many possibilities, and you can even it could even be possible that like the lightest one in the KK tower is actually dark matter itself. So yeah, those are not necessarily. I mean, the stasis scenario and dark matter production scenario, those are not necessarily connected to each other.
Okay, great. Thank you, Faye.
No problem. Thanks.
Someone else?
Yeah, questions from the public. So let
Mhm.
me read it. It says, could you explain a bit more why a state of stasis occurs in cosmology?
Oh, I'm sorry. Why stasis occurs in cosmology?
Exactly.
Oh, this yeah, I think this is the one that I already explained during the talk. Yeah, but even I mean, there can be many different ways to generate the initial abundance of the states in the tower. Like for closed client states, you can think about the misalignment production. Then you can introduce some mixings between different states in the tower. Then you can populate like the entire tower. Yeah, or you can think about like the decay of inflatone, or you can have some matter fields that freeze it out one by one during the freeze out process, and then they later become dominant in the universe and then start to decay. So there can be many different ways to generate all the states.
Okay, thank you.
Okay. Yeah. Thanks.
Somebody else? Faye, what about this tower of scalar fields? Could be there dark matter, or what happened with this tower of scalar fields that could
Oh,
generate?
yeah. Are you talking about mm, um the third model that I mentioned, where we have like
Exactly.
oh yeah. So in that particular scenario, we were only yeah we were only thinking about the transition from the overdamped motion to underdamped motion of the tower. But of course, once you have something like that happen, you still need to restore to the standard scenario where you have radiation domination and BBN, all those things happens, right? So um, eventually you will need to introduce some kind of operator for all these scalars to decay away. So the scalars can decay away into a thermal bath, and then yeah, dark matter can be generated through the thermal bath, or dark matter can be generated through the decays of some of the particles. Yeah, so those are not specified in our model. Yeah, it's something that yeah, you can build your own model to be compactified to be compatible with the scenario. Yeah,
Okay, thank you.
okay. Yeah, no problem.
So, anybody else? If no, we thank again Faye Huang for this amazing talk.
Thank you for the opportunity. Yeah.
Thank you so much.
Mm.
See you next week.